sharing the screen. Okay. Okay, there's another notes packet up front. It's a midterm review thing. If you want the physical copy, it's up front. Electronically, it is in our 04 folder under midterm practice.pdf. And if you look at it, it just has a bunch of true and false things. The true and false focuses for this handout focuses on the very earliest stuff that we talked about. If it loads, like the PLA algorithm and how that, and finite hypothesis classes, things like that, and how that's all comparing to the most recent stuff. So tying into that. We may or may not get to that today. Today, we're going to finish up talking about, where did it go? Here we go. There's a lot of people here. Finish up talking about this SGD paper, large scale learning, the optimization from Leon Bateau. And this is the last thing for the midterm. My sense from just talking to a handful of people is that a lot of people, well, there has been a lot of material for so far in this, for the second midterm. This is the last thing for the midterm. So we could conceivably have the midterm this coming weekend. That was my original plan, but a handful of people have asked for it to be rescheduled. So unless there's a bunch of people who really want it this weekend, my suggestion is that we'll make it not the weekend before Halloween, but the weekend after Halloween, and that'll give an extra week for people to ask questions. And then the format would be very similar to before, with getting it on Thursday and having up to Sunday to complete it. Is this complaints about the timeline? Does that sound better than earlier? Handful of head nods or indifferent motions. Okay, then I'll make it official. And let's go ahead and give it a nice label. Okay, so again, yeah, today we'll finish up talking about all the last material for the midterm. And again, I won't have I won't schedule a midterm review session, but if you all want to suggest times to do a midterm review stuff, then I encourage you to do that on GitHub, and we'll figure out a time that works and have one or more of those review sessions. So again, where we left off, very first part of this whole section of the midterm talking about just statistical stuff, and then we're moving now into the computational stuff, finishing that up, and said that the textbook has a really sort of fast overview of computational things. And so this paper here is going to fill in that gap for us. And again, this paper is a very famous paper. It's at the NeurIPS conference 2018, won that Test of Time award. It was originally published in 2007. And people, this was sort of the paper that first made like stochastic gradient descent the main algorithm that people use instead of gradient descent, or that second order gradient descent. And so that's why we're talking about it, for that historical reason. And stochastic gradient descent remains today like the #1 optimization technique for large scale machine learning things. Where we left off last time, we talked about, well, let's see, another sort of meta thing. Again, one of the purposes of this class is to not just get you familiar with the various data mining concepts, but also to get you able to actually like read new data mining papers as they come out, machine learning papers as they come out. And one of the hard parts about that is that there's a whole bunch of notation, that it's all the same concepts everywhere, but different notation for different authors. And so the main focus of last time was just for us to get sort of a handle on that notation, how it compared this paper to the textbook's notation. And then we started talking about these different gradient descent formulas and focusing on their runtimes and the algebraic sort of properties of these different algorithms. And at this point, kind of neglecting the geometric intuition behind these algorithms and why they might be good things to use. So we'll start today talking, well, then last thing that we, this is right here, there was a note packet that went along with that paper. And this table 2 right here comes from the paper itself, but the paper mentions that for brevity's sake, they leave off all the dependence on dimensionality in their runtimes. And so in this table, we were adding in those dependencies on dimensionality. And so today we'll start our discussion with some geometric intuition about these different algorithms, and then we'll focus on completing this table and completing the discussion of this note packet and the paper. Any questions about where we are, what we're looking at? Okay. There's a very famous picture that I'm going to draw below this table right here about these different algorithms. And there's, again, lots of different pictures that people draw to help get some geometric intuition behind these. But this is the, I don't know, the simplest one to wrap our heads around. So it'll be the one that we start with. So what I'm going to draw here is, I'm going to get my cursor to work. And what I'm going to draw here, there we go, a bunch of sort of oval shapes like these. Technically, these are all ellipses. And the X and Y dimensions of this plot are, it doesn't really matter where the origin is here, but the X and Y are like the, what we're visualizing here is the W space, the parameter space. So both of these two axes together are the parameters. Here we're just looking at 2 dimensions because that's really all that we can visualize. But in practice, the typical data mining problem is in the millions or billions of dimensions. A lot of the, I don't know, other applied mathematical fields think like 10 dimensions is high, but in the data mining world, 10 dimensions is nothing. Like, yeah, I regularly work in billion-dimensional spaces, and it's not a problem for us. But we're just going to visualize 2 dimensions. And then what these ellipses are representing, these are the contour lines of our true loss. Maybe we'll make it the, instead of the true loss, we'll make it the in-sample error, although it doesn't really matter which one it is, of our function G that we're trying to learn. And again, G here has an implicit dependence on the W. And so sometimes people talk about the function and the parameters of that function interchangeably. So people might also say that that's En of W. And the textbook and this paper all go back and forth, treating a function and its parameters as the same thing. And so this right here would be the optimal parameter down here in the middle. This is the one that we're trying to get to. And these contour lines are like the function is getting bigger and bigger the farther away that you get from this minimum. And these are the constant value curves. So everywhere on one of these ellipse lines is constant value. And the idea of any of these algorithms is that we want to find this minimum. And so we're going to start somewhere on this curve. We'll make this point right here our starting spot. And we'll start talking about this gradient descent algorithm. that in gradient descent, we take the gradient of this E in right here, this thing that we're trying to optimize, and we step in the direction of that gradient. The gradient is going to be orthogonal or perpendicular to the contour line that we're currently at. And so the gradient will go something like this. And this particular, so I drew the distance like that, just so it happened to line up nicely with the next contour line. But the actual distance here is dependent on that hyperparameter. So these things, W, the things that we're learning are parameters. The hyperparameter is the thing that we are, as users of the algorithm, we're selecting. And the hyperparameter for all of these algorithms have a hyperparameter of what is our step size. I believe it is gamma. The notes above, gamma hyperparameter determines the step size. And ideally, we would want like the perfect, just right gamma that's going to get us into the minimum over here. But in high dimensional spaces, hard to do arbitrarily. And so tuning this gamma perfectly is a little bit of an art, but you want it, I don't know, this is our gamma, this is how big it takes us. And then it'll take us from here. Our next iteration, again, perpendicular to the contour line. So something like that maybe. And each time, if you go perpendicular to the contour line with a small enough step size, you're guaranteed to get closer and closer to this minimum. And so the gradient descent algorithm typically has a graph that looks something like this. The steps get closer and closer together as the gradient gets smaller and smaller. The actual size that we step is the product of this gamma and the norm of the gradient right here. So as we get closer and closer to the minimum, the norm of the gradient gets smaller and smaller, and you naturally approach the minimum here. And here's our convergence rate, this rho value right here. Rho is the accuracy. So if each one of these points right here, rho is the distance from that point to the minimum. So rho is getting smaller and smaller, and this is the bound that we have on how many iterations it will take to get within a certain accuracy rho. Any questions on gradient descent? Okay. So stochastic, second order gradient descent, the difference between second order gradient descent and gradient descent is that whenever you have a quadratic looking function here, quadratic functions in high dimensional space form these ellipse contour lines, then second order gradient descent can instantly take you from wherever you're at down to the minimum in a single step. This, let me write it out explicitly here. Red is the gradient descent. And then we'll use green for second order gradient descent. Second order gradient descent will take us immediately to the minimum in a single step, since I drew this as a quadratic function. For non-quadratic functions, it's not a single step, but it's say it's exponentially faster than gradient descent because it has this extra log term in the number of iterations that it takes. It's log one of a row instead of just log of one of a row. So it's significantly faster. The only downside to the second order gradient descent is that we have this additional dependence on the dimension. It's quadratic in the dimension instead of linear in the dimension. And that's due to the fact that we're having to build up a matrix and do the matrix multiplication. In practice, for real world problems, gradient descent very, very rarely used, and second order gradient descent almost always better than gradient descent. But the double log here almost always sort of dominates compared to the d squared. Let's go back here to remind ourselves. Yeah, so here's the gradient descent algorithm. That gamma right here, that's our step size. We're just multiplying by this is a constant here. So each iteration is faster. Down here in second order gradient descent, instead of having this constant gamma, we have this matrix gamma t somehow determined from the data, from the loss function that we're trying to optimize. And so our step size is more sort of determined automatically for us. And we get that faster convergence in terms of the number of iterations. Stochastic gradient descent, the key idea here was that up here in both of these functions, we had this summation that we were doing. And so that summation made each iteration slower. And in stochastic gradient descent, our goal, or what we did, was we just got rid of that summation, so each iteration is faster. But now each iteration is only an approximation of the true gradient, because we're only looking at a single data point at a time. So roughly half the time, a little bit less than half the time, we'll use orange here for stochastic gradient descent, we'll be moving away in the wrong direction. And so we sort of go bounce all over the place like this. And just approximately on average moving in the right direction, but there's no guarantee that on any individual iteration we're moving in the right direction. But eventually we'll be considering all the data points, and eventually each iteration on average will take us in the right direction, and so eventually we'll converge. The fact that we're using only a single data point at a time, like this very random approximation of the true gradient at each step, means that our convergence rate in terms of the number of iterations is really slow, 1 over rho instead of the log of 1 over rho. Log much, much faster, log much, 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 much faster than 1 over rho. But then the advantage here is that the time per iteration has no dependence on the number of data points and only depends on the dimensionality. So this orange one here is SGD. Any questions about? Yes.
I had a question about the step size. What determines step size? Because I kind of thought that it's just going to be how does step size factor into our model?
Yeah, so the question is basically everything about step size. So here the step size, literally what it is it's this gamma in this equation right here. And this gamma, so it's a scalar value, and it's something that is determined by the user of the algorithm in advance of running the algorithm. So we pick gamma, and that's going to scale our gradient right here by this particular size. The book, I'm going to switch over to the book here, has a couple of other illustrations which talk a little bit more about the step size and the intuition behind picking the step size. This is a single dimensional slice of the loss function that we were looking at before. So now the x-axis here is single dimensional, and the y-axis here is the actual error, this E sub n, what the contour lines were representing before. This gamma right here is this eta right here is what the gamma was on the other paper. So the eta is our step size. And if your step size is really small, then you're guaranteed to eventually hit this, this minimum here and get there sort of always continuing to go in the right direction. But you might take a long time to do that if your step size is too small. If your step size is too large, then you might overshoot the minimum and be bouncing back and forth a lot like this. You'll notice that in both cases, like we're starting at the same point right here. And so the gradient is the same value. It's just being scaled by a different size. And so that's why here we're scaling it by a large thing. So we're stepping over a large way and happen to be stepping over the minimum W value. The ideal sort of situation is that, yeah, there's just right step size where we're taking moderately large steps, but not too large of steps. For the purposes of the midterm, like having a good fluid understanding of the step size and its implications is not important for the midterm. It's not going to come up. But you will have another programming assignment where you'll have to fiddle around with the step size to get it just right to get the convergence. Does that answer your question? Yeah.
Does the step size like scale itself?
Yeah, so the question is, does the step size scale itself getting smaller? And the literal answer is no, that if you're talking about the step size is just this eta value or just the gamma value in the other paper, then that's typically picked as a constant for the gradient descent or stochastic or the second order gradient descent algorithms. Any of the non-stochastic versions, it's typically picked as a constant. But you can still see that somehow the step size is getting smaller and smaller each time, or the actual distance that we move is getting smaller and smaller. And that's because the distance that we move is the norm of the gradient times the step size. Going back to the actual equation right here, the update that we have right here is the step size times the gradient. So if you're really, really far away from the norm, it turns out the gradient is guaranteed to be large for these convex functions that we're optimizing. And as you get closer and closer to the optimal, the gradient right here will get smaller. The gradient of your loss will get smaller. And so gamma doesn't change, but the product of gamma times this whole thing right here does get smaller and smaller as you approach the optimum. Did that answer your question? Yeah, these are, I don't know, lots of things in this class are very abstract. This is an example of one of them that we can sort of visualize these things in 2 and 1 dimension, but again, in practice, we're working on million or billion dimensional problems. And so trying to visualize that somehow doesn't really make sense. And so the important thing, the thing that's actually going to be like helpful for you in solving problems in this class, whether it's programming problems or midterm problems, is understanding these algebraic properties of the algorithms. But this is, I guess, the low dimensional geometric intuition. There is no high dimensional geometric intuition. Good questions. Any other questions so far? Okay. So at this point, what we've talked about this paper is all stuff that was well known up to 2007 when this paper was published. And so all the stuff in up to section 1 and 2 was all review, sort of background information for the people who were reading this paper. Section 3 here is the stuff that is the most important for our exam and the most like at the time interesting to the people reading it. So again, there's a bunch of notation that we'll have to talk about how it compares to our notation, and then we'll get into these like the key insights of this paper. So the first thing here, so as a reminder, this E, anytime you see the, why did it do that? Anytime you see this E in the Leon Bateau paper, E by itself is, where did it go? Sorry, there we go. This E right here, that is the true loss, or what the textbook calls E sub out. And what this paper calls E sub in is what the textbook calls E sub in. And now that I say that a lot, I realize they're pronounced the same. But E sub letter N means it's trained on, that's the in sample error trained on in data points. What is that? What is that error evaluated on in data points on the training sample? And the E sub in right here, this in being the in sample error in the data set. That star, anytime you see a star in a paper, star somehow means like the optimal. And in the textbook, the true data function, the optimal data function was called F, is F star in this paper. Again, this paper is using this fancy F as the hypothesis class right here instead of H. So that's why all their examples from F from the hypothesis class are going to be F's instead of H's. So they add the star here to make it, to clarify that it's the optimal. Here, when we have the subscript of F like this, then this is the best hypothesis possible in our particular hypothesis class that we're selecting from. So this is something that's not defined in the textbook anywhere, but this is the best hypothesis class. Best hypothesis in the hypothesis class. And again, it doesn't depend on the data anywhere that this E is the true error. So this is something that we can't possibly know. We can only estimate it somehow. And then this F sub in right here, this is actually on the data set. It's E sub in down here. So this F sub in is what the book usually calls G. This is, and what I've sometimes called the empirical risk minimizer, the ERM. This is the thing that we can sort of realistically actually optimize. And we said that for finite hypothesis classes, we can compute this argument exactly because we can actually try every hypothesis in F here. But the whole point of what we've been talking about the last week or so is that we're working with infinite hypothesis classes. We can't apply them all. So we're using this, like these gradient descent algorithms to do F tilde is the output of our actual algorithm. Whether that algorithm is gradient descent, second order gradient descent, stochastic gradient descent, whatever it happens to be. And so this formula right here just has the relationship between, so again, Fn is the best empirical risk minimizer, what we're trying to compute. F tilde is what we actually compute. And then this rho thing again is that like the error of our optimization algorithm, that if we were to run gradient descent or whatever it is for an infinite amount of time, that this rho would go to 0. And so the error of F tilde would go to the error of F sub n, that they would be the same thing if this goes to 0 because we ran our algorithms for an infinite amount of time. So all that's just sort of taking a look at the notation here. Any questions about any of the notation? Okay. Then this formula right here is going to be the key insight that's provided by, or the first key insight provided by this paper. Here, these script E's, these are somehow error terms. There's going to be 4 of them that we'll see here. And this fancy E is the expectation. Turns out that all of these things are true statements without having the expectation out in front of it. And that's not actually a prereq for this class. So we'll just scribble it out on all these things. That take out the expectations and everything remains true about this paper. quick historical aside, not something that you have to know, but the reason that the expectations are in here is because at the time in 2007, the only like theorems that we had about stochastic gradient descent were in terms of expectation, but at this point we have more robust convergence proofs about stochastic gradient descent. And so at the time, everybody was always used to talking about in terms of expectation, but it's not actually needed. So this equation 6 right here, it's a big equation. There's a lot of fancy letters in it. How can we go about figuring out why this is true and why he wrote it like this? So the first answer, why is it true? It's just immediately from the definition right here. So this E right here, this excess error, let's first think about what it is. So this F star again is the best possible optimization or the best possible hypothesis that we can have. The F tilde sub n, that's the hypothesis that we actually have. So the excess error here is like how much worse is the hypothesis that we actually have from the best possible one. And we want that to be small. We want our excess error, we want the error of our hypothesis to be as close as possible to the true hypothesis. In order to get this equation 6 down here, so you can see there's this F sub n, here's F sub n, the tilde F sub n, there's the tilde F sub n, both those terms are positive. Here's the F star right here, EF star, there's the, do a different color, green. Here's the EF star. Here's the EF star, and you'll notice that both of those two things are negative. Both of those two orange things are positive. And then there's a bunch of terms that are just added and subtracted to the right-hand side of this equation. So like this F star sub F right here, there's a positive version of the term. Here's a negative version of the term right here. So those two things just exactly cancel out. And similarly, do the last one in red here. This is a positive version of this negative term right here. So those red things cancel out, those blue things cancel out, and we get, if you did that canceling out, you'd get exactly this excess error recovered. So the reason for adding in those extra terms, those pluses and minuses, is it allows us to group things together into things that we can either know directly or things that we can to analyze using all the statistical theory that we've talked about so far. Any questions at this point? Where this 6 came from?
Clarifying what the definition of excess error is. This is specifically on our training data. We have the hypothesis we chose versus the ideal hypothesis for this training data.
Yeah, that's a good question. So here, when we have the E by itself, this is the out of sample error. So this is the true error. So this is the best, when we talk about the best possible hypothesis and compare what's our output, what's our value, our error of our particular algorithm right here compared to the best, we're looking at the true error or the test error as a proxy for the true error. This here, this F tilde sub n, this is dependent on the data. The thing that we're passing to evaluating on E is dependent on the data, but the error itself not dependent on the data. Did that answer that?
Yeah.
Okay, so 3 breakdowns of these terms. First one, they're calling the approximation error. This one appeared on your programming assignments on that Jupyter notebook that was due over the weekend. And so this is again, the F star sub F. This is the best error on our hypothesis class, independent of the size of our training set. So as the size of the data set goes to an infinite amount, what's the best that anything in that hypothesis class can possibly get? So this, I'll write that just independent of the training set. And again, in the limit, as n goes to infinity, then f sub n will go to f star sub f. And this thing right here just follows immediately from the definitions of these two terms. Their sentence here, the approximation error can be reduced by choosing a larger family of functions. So that means that if you have two hypothesis classes, and we've had very similar arguments to this in the past, but if we have two hypothesis classes, say F1 and F2, where F1 is a subset of F2, then we're guaranteed that the approximation error, you approximate with F2 substituted down here of F2 is going to be less than or equal to the approximate of F1, because every hypothesis in here is also in here. So in the worst case scenario, the best hypothesis in F2 is going to be the same as the F1, but we also have more hypotheses that we can select from. So if for whatever reason we know that we need to reduce our approximation error, we do that by selecting a hypothesis class with a larger VC dimension, or a hypothesis class that is somehow a superset of our current hypothesis class. A lot of subtle things in there. Any questions about that? Maybe let's step it back for a second and talk about like how do people like in practice talk about these approximation errors and things. So like if you're say talking to somebody at Google who is a data mining machine learning person, maybe in a technical interview situation, then people will just say things very informally, like I need to improve my approximation error. And you just know that that means, okay, I need to pick a, like if let's use the polynomial kernel and go increase the degree from 2 to 3 or something like that, because we know that that increases the size of our hypothesis set, increases our VC dimension. At this point, that's our main tool for increasing the approximation error or decreasing the approximation error, is using the polynomial feature map. Polynomial will decrease, yeah, and then using either the PCA or random features will increase our approximation error. And again, that one sentence in this research paper and in other research papers covers that like 2-week section of the midterm. And it's just implicitly understood that you know how to go as much in depth into that as you need to understand what it's saying. So the next thing here, I think a little bit more interesting even, is this estimation error. And so again, that's this middle term right here. And this says it measures the effect of minimizing the empirical risk instead of the expected risk. And again, this is something that is for somebody who's an active data mining practitioner is intended to be obvious. But one of the things that's confusing about this here is that there is no E sub n anywhere in this estimation error right here. All this quantity here only talks about the true error and not the empirical error, not the in-sample error anywhere. And so I want to very briefly give us a bound on this estimation error using the things that we already know. And what that looks like is that, so by definition, our E estimation error is equal to the E of F sub n minus the E of F star sub F, like that. And so this this orange stuff is just exactly this thing right here. Whoops, that's the wrong one. It's exactly this thing right here. And then we're going to use that same trick that he used on equation 6 right here of adding and subtracting a key term. And the key term that we will add and subtract here is that we'll subtract from right here the E sub n of F sub n, and we'll add it over here, plus the E sub n of F sub n right here. And now this thing on the left-hand side, if you squint really hard, is something that we saw before in the textbook, that this is what the textbook called the generalization error. This is the true error right here, the true error. So what textbook calls E out. In the green right here, I'll write how the textbook writes this. E out. Again, the F sub n is what the textbook calls G. Minus this E sub n is our also E sub n, just the n sample version instead of the letter n version. And again, of this G value right here. And this is the thing that we talked about with the VC dimension in order to provide a bound on this. And that bound was O of square root dVC log n over n, like that. So with that translation, I was able to apply a bound on this left-hand term right there. It's a little bit tricky doing the same thing on the right-hand side, because the key thing about our generalization bound, our VC dimension bound, was that we had to have the same hypothesis in here in both sides. And over here, we have two different hypotheses. We're at the comparing the in sample error right here to the out of sample error, but it's of two different hypotheses. And so I have a further claim that this thing in red, less than or equal, keeping the first term exactly the same, E F star sub F, like that, plus, and then E sub n of F sub n. That's exactly what that's not what I intended. There we go. E F star of F, like that. And so in particular, I'm claiming that this thing up here is less than or equal to this thing down here. And that, if you go up to the definitions, it immediately follows from the definitions that this Fn is the minimization over the in-sample error. This thing is a minimization over the true error. And so those things are going to be closely related to each other, but the minimization over the in-sample error guaranteed to be smaller than the minimization of the true sample error. And now at this point, we have something that we can apply the VC dimension bound to O of square root D log n over n, like that. And so this whole E estimation error thing with all these two things together, it's the same on both sides. And so it's bounded by O of square root D log n over n. And again, this D, sometimes I wrote dVC, the VC dimension, that D is the VC dimension of the problem. Yeah, if the details of all of that manipulation is not 100% obvious, that's okay. the source or all the motivations behind all the steps or all the reasons why all the steps are true come directly from the definitions of the various terms. But the key point, the key takeaway is that this estimation error is bounded by our VC dimension theorem. And so that's, again, this sentence up here, why they're saying it, that it measures the effect of minimizing this empirical risk instead of the expected risk. That's exactly why we were talking about the VC dimension in the first place. And so we get the same exact bound. Any questions on that? This last term, this optimization error, so it's the difference between our Fn tilde minus Fn, the difference between the thing that we're actually optimizing and the empirical risk minimizer. And this is what, scroll up real quick to do exactly what this equation here was relating those two things by. So this optimization error right here, that's equal to the rho value, the thing that we can minimize by making our training algorithms, our optimization algorithms run for a longer period of time. And let's see, the key idea of this paper is now that we have somehow broken out our excess error, fundamentally we want our excess error to be small. But this paper was the very first one to include this optimization term inside of this excess error. That people were talking about this VC dimension trade-off before, like we've been talking about. But before 2007, nobody was talking about this optimization term and how it affected us statistically. And in this 3.2 section, well, here you can see this is exactly what we talked about before. So they broke up this is just repeating equation 6 that we had above. Just using the shorthand version for all of those different terms. And now we plugged in here, this is our VC bound on the estimation error. Bound. On that. And the row was just by the by definition. And the key thing is that in order for us to make this epsilon go to a small number, we need all these terms, all three of these, to decrease at the same rate. That previously people were saying, oh, I know how to make, previously everyone said, there's supposed to be two words right there. Everyone said, let's make rho go to 0. The best algorithm for making rho go to 0 is second order stochastic gradient descent because it has log 1 over rho as the runtime. And so SGD best algorithm, but there's no point in making rho go to 0, making it go to a really small number if our other two terms have really, really high error still. That the error of those two terms will dominate whatever this error is. And so we're potentially wasting a lot of computational power that we don't actually need to be doing. And so this equation 8 right here and equation 9, anytime you see this tilde, A tilde B, that's equivalent to saying that A equals theta of B in our big no notation, that it's basically equal to each other asymptotically, that it's both upper bounded and lower bounded by B. So we're setting all these things to be asymptotically equal to each other, and then we'll solve for what's the optimal values to make our all these terms actually decrease at the same rate instead of making this thing decrease faster than these ones. It's a little bit confusing right here that here this alpha sets it can be anywhere between 1/2 and 1. For our purposes in binary classification, we saw that the VC bound alpha is always equal to 1/2. And then I mentioned that the book talks about this other bound for the ordinary least squares case, the alpha equal to 1, that happens to correspond to the ordinary least squares, alpha equals 1 for the squared loss. But you don't need to know about that. You can just assume that the alpha is 1/2 for all of our purposes, and that'll be fine. So assume this. So again, with this table up here, we talked about these first 3 lines, and the first line, runtime per iteration, the second time, the total number of iterations, third line is the product of these 2 things above. And if you're trying to get your row as small as possible, then the row, the second gradient descent, always going to be the best thing because it has the best dependence on row right here. But if you're really caring about the excess error, then this bottom row is the amount of time it takes you to achieve a particular excess error. And again, that excess error is this epsilon right here. And we'll get that result by setting each of these terms, setting rho equal to epsilon. If you set rho equal to epsilon, substitute that in for SGD, 1 over rho gives you 1 over epsilon. Here, if you have log n over n to the alpha, set it equal to epsilon. I'm going to write that out over here. In order to get the 4th row, set rho equal to epsilon and square root log n over n equal to epsilon. And you plug those things. So here, that's obvious what rho is equal to. Solve this for n, then that's log n over n equals epsilon to the let's see, yeah. In that case, it'll be epsilon squared. More generally, if we had this log n over n to the 1 over alpha, or sorry, to the alpha. So that's what they actually have in the paper. This is specialized for our binary classification situation. Then that'll be epsilon to the 1 over alpha right there. And then solving for n, it's hard to do that in the non-asymptotic case. In the asymptotic case, turns out to be not too bad, but requires weird calculus that we don't care about. And you get that n is equal to, or n is, I'll write it that way, asymptotically equal to epsilon to the -1 over alpha log 1 over epsilon, like that. If you plug in these values for n, plugging in this value for n and this value for epsilon into this 3rd row up here, that gives you this 4th row right here. The key things that you need to make sure that you understand, there's a lot of small, subtle technical details here that's easy to get lost in. But the key things to understand is that this right here, this bottom row, is the amount of time that you need to run. This is the actual amount of time to run your algorithm. Because up here, so time to accuracy row, if you're setting row to be something very, very small that's like close to 0, then this is what you need to know. But in practice, we don't want to set row to something arbitrarily small. We want to set it equal to our the error of all of our other terms. And when you set it equal to the error of your other terms, make your optimization error the same as your statistical error, then this is what you get right here. Yes. So one last leap for us to make, but this is a good spot to take a break. And if you have questions about anything that's happened so far, to ask those questions. Okay, so then the last leap for us to make is these are our 4 final run times down here. And actually, if we can go ahead and substitute. One of the things I guess we didn't do is put in our dimensionality dependencies down here. It looks something like d squared plus d times all of that, d squared. But ask ourselves, which one of these things is the fastest? Which one of these things gives us the smallest number? And so this is an exercise in asymptotic notation and figuring out which thing is the smallest asymptotically. And we could plug into Wolfram Alpha and do a whole bunch of manual calculations with that to figure it out. The easiest way to do that, though, is just to I don't know, plug in some numbers, and you'll see that in fact, whether alpha is 1 or 1/2, this thing over here, this right here, is always the fastest, asymptotically the fastest. So in particular, 1 over epsilon is strictly upper bounded by say strictly smaller than these other 2 terms, 1 divided by either 1 over alpha log squared 1 over epsilon. And I guess I already wrote out this one, so I'll write out the other one. And 1 over epsilon 1 over alpha log 1 over epsilon log 1 over epsilon. And our standard asymptotic notation, that would be that these are sorry, not omega, but these are upper bounds. The upper bound, again, though, is not like a doesn't imply necessarily strictly, but it is in fact strictly smaller than these things. And so because of that, in the large scale case, in the case where you are limited in the amount of computation time that you have to run, stochastic gradient descent is going to give you a better answer than gradient descent or second order gradient descent. Even though these 3 things are better optimization algorithms, just in terms of how fast they converge to the true answer, these things over here converge faster. That if we were only looking at the 3rd value over here, those 2 things are smaller than this. But when we're actually considering that we don't need to converge to the true optimum, stochastic gradient descent gives us good results. Coming back to this geometric intuition picture over here, my thing is too sensitive. One way to think about it is that like anything inside of this second circle right here is really good enough for a problem, that you don't have to get to the true optimum. You just have to get kind of close to it, because like the true optimum of the EN is not the true optimum that we're actually trying to minimize. And so just as long as we get anywhere close to it, then we're good. And SGD is going to get us somewhere close to it pretty fast. This is extremely surprising to people at the time. Now everybody just takes it for granted. For any sort of remotely large scale problem, everybody uses stochastic gradient descent. For smaller problems, people still use second order gradient descent, because if you're not limited by computation, you may as well make your optimization error as small as possible. But if you are in any way limited by computation, very, very surprising to people that stochastic gradient descent was the way to go. Any questions about that? That's the key fundamental insight: large scale learning, stochastic gradient descent, best optimization. Okay, so then for the midterm, what do you have to know about all of this? Well, there's some example problems down on the next page. And so this first example problem here says we're training logistic regression model using the polynomial feature map with a very high degree and a small number of data points. So if I have the polynomial feature map, write it out. Poly feature map in high degree. Is the dimensionality of my problem going to be large or small? Yep, large. Why? Yeah, so the purpose of the polynomial feature map is to increase the dimensionality of my problem, to increase my VC dimension, and a high degree is going to increase it higher than a low degree. So because of this right here, our D value will be very large. Yeah, so the question is, there's a lot of D's floating around here. Is this particular D the same as the DVC? Yes, so here, this would be the, we could be talking about the VC dimension of our problem. In the context, so the VC dimension is specifically for the context of talking about the estimation error or the approximation error. If we're talking about the optimization error and the runtime of the optimization, then the D is this D right here, which corresponds to, sorry. So this D in our table right here that we're filling out corresponds in the gradient descent algorithms to the size of the gradient of our loss function. And it turns out that for logistic regression, whatever feature map you're using, the gradient, the size of the gradient, this D right here, is going to be your VC dimension of the problem. Not in general the case for every loss function, but for logistic regression, that's true. So this is the VC dimension, but more importantly for our problem, it's the dimensions of the gradient. And they're asymptotically equal to each other. I'll do it with the tilde to say that the VC dimension is asymptotically the same thing as the dimension of the gradient. We're talking about the runtime of our algorithms. So runtimes, so if I write it out just in terms of the D, ignoring all the other things, then gradient descent is O of, and it actually, all of these things are thetas, D. 2 gradient descent is D squared, SGD, theta of D, and 2 SGD, theta of D squared, like that. And since D is very large, I can cross out, I can eliminate these two as possible algorithms. They'll be slow because D large. So now determining between gradient descent and stochastic gradient descent, it's the number of data points that's going to be the most useful thing here. That stochastic gradient descent does not depend on the number of data points. Gradient descent does depend on the number of data points. So the run times, again, this is just going to be in terms of n down here. Gradient descent is theta of n. SGD is theta of 1. And so this thing down here is always going to be smaller than this thing up here, no matter what the value of n is. And so if you said you were going to use SGD for that reason, that would be an okay thing to do. That wouldn't be incorrect. But really the best answer here is that since we're not limited by computation at all, since we have a small number of data points, then making this thing a little bit more explicit with the runtime of theta of n log 1 over rho, theta of 1 over rho. We may as well make rho to go to 0, not limited by computation. Because n is small, so very few data points for us to consider. So may as well make rho go to 0, and that will imply that I would pick gradient descent for this problem. But if you said that SGD was what you would pick because this is just from the perspective of n, this is going to be better, then that would be an acceptable thing to say too. Yeah, so the question is, there's a lot of runtimes listed here. What's all the difference? This up here, so these ones in green, only in terms of D. These ones here, only n, and these ones here are in terms of both n and rho.
They all came from that.
And they're all just copied down from the table above, just only considering one variable at a time, thinking about the others as being constant. We could think about them all at once, and the logic would proceed the same way. But it's easier just to think about the one at the time. Good question. Any other questions about this problem? Okay, so before I mentioned sort of offhand that nobody in practice uses gradient descent. In practice, people use second order gradient descent for small scale problems and first order stochastic gradient descent for large scale problems. But here it seems like maybe we have a situation where like first order gradient descent is the thing to do. But the problem here, or the reason why nobody uses gradient descent, is because this is a situation that you never want to be in. What we have right here. VC theory predicts very bad statistical performance for us. Very bad statistical performance because, again, our DVC, our VC dimension, is large, and it's extremely large because we're using the polynomial feature map, and with a high degree that it grows very, very fast. So DVC is larger than the number of data points by a lot. And so our bound on the generalization error, when people talk about the statistical performance, they can be talking about any one of these errors, the in-sample error, the out-of-sample error, the excess error, the approximation error, the estimation error, the optimization error, so many different types of errors that people can be talking about. But 90% of the time, people are talking about the generalization error when they talk about statistical performance. And so in particular, the E out of G minus E in of G, whatever we learned through optimization, we said that that's less than or equal to the square root of DVC log in over n. And based on this statement over here, this is going to be a number that is so that's just a really big number. The textbook mentions that in practice, a good rule of thumb is that your VC dimension should be like, or sorry, the number of data points should be 10 times the VC dimension. N should be 10 times DVC. And that's a good sort of starting place when you're working on a problem, picking out which hypothesis class you're going to use for your particular data set. And so, yeah, because DVC is much, much bigger than N, we know that this thing just, this bound's not going to mean anything for us. And it turns out the only situation where gradient descent might possibly be better than any of the other algorithms is in this situation where statistical performance is bad. So that's why gradient descent never used in practice, only second order gradient descent or stochastic gradient descent. The next two problems on this page are following similar reasoning, somehow combining this thinking about runtimes, which algorithm you should choose for a particular problem, and statistical considerations. But we will stop here for today, and that is everything that you need to know for the midterm. So good luck on your studying, and if you come up with any questions at all, I'd be happy to help you work through them. But that's it for today.
Thank you.